So as you've probably already noticed, calculating the gamma probability problems by hand using the gamma distribution is pretty tedious, and so using software can be really helpful for us. In this example, I've set up some code in which we will be able to use RStudio to solve probability problems for gamma distributions. The first thing that I've done is I've defined alpha and beta. So these are the parameters in a gamma distribution. I'm going to run these lines. So alpha is equal to 3 and beta is equal to 12.4. Then if I want to look at the average and standard deviation of the gamma distribution, that will be by definition alpha times beta. So I'm just going to run this little line here, and that's 37.2. And the standard deviation by definition is the square root of the variance, which is alpha times beta squared. So I'm going to run that. So the average is 37.2 and the standard deviation is 21.477 for this particular gamma distribution. Now, I'm going to set up the problem with an x value of 50. So I'm going to find the area that falls below 50 and the area that falls above 50. So I'm going to run that line. You can obviously change this as much as you want. Now I want to draw the gamma distribution. So the first thing is that I've set up a range of values, and it starts at 0. By definition, the gamma distribution has a lower bound of 0, but its upper bound is infinity. And so that's really not possible to see on a graph. So here I have instead just made the graph go out to 5 standard deviations past the average. And so that is what this upper bound is. Now this d gamma will give me the density for each value of the range, and this will then draw my graph. By plotting it, I will be able to see then the distribution of, or the gamma distribution. Whoops, one more time. I can then see the gamma distribution with an alpha of 3 and a beta of 12.4. So pretty cool. Now I want to add in the area that falls to the left of my x value. That's going to be the cumulative area, so that will be these lines here, and then add the area above. And I've just shaded that in as gray, and we can see that a large portion of the area is below 50, so we should expect a pretty large probability. So what we can do to use software to calculate that is use this command p gamma, where p stands for the cumulative probability and gamma is then the distribution that we're interested in. X is the value. Recall this is 50 from above up here. Our alpha will be 3, and we define that above. And then we have something called the rate parameter. All the different software and different fields parameterize the gamma distribution slightly differently. Some use what's called the rate parameter and some use a scale parameter. We're using a scale parameter, so that's what beta is. However, we need to define in R the rate parameter, which is simply just 1 over the scale parameter. So here it's just 1 over beta. So you can just follow along with this format whenever you want to do it on your own. So let's go ahead and run this and see the probability that x is less than 50. And that is 76.65853. And that really makes sense because this is a large portion of the data. Now, if we were to run the second line, 1 minus that same function above, we will get the area that falls above the value of 50, which is 0.2334147. So it's the exact complement, and that also makes sense because that is this smaller portion. All right, so now let's use the command q gamma, which this gives us the quantile or percentile. If I want to find the 50th percentile, then I first put in my percentile as a proportion, then I put in the alpha, then I put in that rate parameter again, which again is just 1 over the scale parameter, which is 1 over beta. So I can run this line and I'll find the median of my distribution, which is 33.15835, which is just slightly less than our mean. Now, one other thing that you can do where software becomes really important to use instead of doing this by hand is when we have an alpha value that is not a whole number. It's not an integer. So let's say we were to change this to 4.2. How does that then change, one, the look of the distribution, and two, how does it then change the way we would calculate it by hand? Well, it gets really messy because of that gamma function in the gamma distribution function. So we can then calculate a lot messier probabilities when we're using software. So in this example, when I change the alpha to 4.2, I get a slightly different looking distribution. But more importantly, then the probabilities change and it's just seamless. So it's a lot easier to use software to find probabilities than it is to do this by hand.